So in this lesson, we will discuss about the BPSK reception. So the receiver of binary phase shifting signal. So already in the previous video we have discussed the transmitter. So in the transmitter it is a balanced modulator or a product modulator. There your message signal, that is BT or data signal, is multiplying with the carrier pulse. Carrier is nothing but root 2 ps cos omega 0 t. So that your output will be Bt into root 2 ps cos omega 0 t. This is the one we are going to transmit. So this is your transmitted signal. This is your transmitted signal ST. So this is the one signal we are going to transmit through the channel. So the signal transmitting through the channel is Bt into root 2 ps cos omega 0 t. So what happened when it is passing through the channel? Obviously everybody knows that the noise will be affected, isn't it? This signal will be affected by the noise. So now we are mainly dealing its main noise. If it comes to the phase, you may interpret it as wrong at the receiver. So the noise signal that is affecting to the phase will be having an effect over here. So suppose that when this is passing through the channel, it is affected by the noise, and at the receiver, say we are receiving a signal with a slightly different phase than that of transmitted signal. This is a transmitted signal phase, root 2 ps Bt cos omega 0 t. When it passes through the channel, noise is affected and a phase difference, a change in phase will happen to this. So now at the received signal, so this is now your received signal. Your received signal is root 2 ps Bt cos omega 0 t plus theta. This is because of this phase difference is because of the noise. So now this part will be dealing with the receiver. This part will be dealing with the receiver signal. So now we will see in detail that. So as I told you, your received signal RT is equal to root 2 ps into Bt cos omega 0 t. This was the transmitted signal plus theta. There is a phase change when it is traveling through the channel. A noise associated, noise that is affecting this signal is theta phase change. So now after reaching at the receiver, for getting back your what is your transmitted Bt, whether it is a 1 or a 0, that is the information you have to get it back, whether it is symbol 1 or a symbol 0. So for that, at the receiver here, first we need to locally generate the carrier signal. So we have to locally generate the carrier signal over here. So for that, you have this arrangement. You have a square law device, a band pass filter and a frequency divider for that. It is only for recovering the carrier signal for the purpose of your demodulation. So your received signal is first of all squared, because RT is the received signal. This square law device will square the received signal. So now you have here received signal is cos omega 0 t plus theta. When it is square, you know that cos square theta. What is cos square theta? We can again write it as 1 plus cos 2 theta divided by 2. It's a trigonometric expression only. So you can write as cos square theta as 1 plus cos 2 theta by 2. So similarly, when it comes over here, it is cos square omega 0 t plus theta, it will come. So you can rewrite that expression as, see, cos square, I can rewrite it as cos square omega 0 t plus theta. This I can write it as 1 by 2 into, what 2 I taken as 1 plus cos 2 theta. That means it will become 2 times omega 0 t plus theta. 2 times omega 0 t plus theta it will come. So here this the received, after squaring, you will get it as it's omega 0. Now it becomes 2 times omega 0 after squaring, isn't it? So the signal coming, the next one is a band pass filter. So what the purpose of this band pass filter? Whatever DC component are there, here 1 by 2, it is a DC component. Or even we are not interested in root 2 PS or BT over here. This is only, this part is for recovering your carrier signal. This part is exclusively for carrier recovery. Okay, this part is exclusively for carrier recovery. So in that case, we are not interested in root 2 PS or BT or whatever things. Only we are interested in the carrier signal. So amplitude is not of our importance now. So it's cos square omega 0 t plus theta after coming out from the square law device. Again I can rewrite it as like 1 plus cos t 2 omega 0 t plus theta by 2. Now see here, your frequency or omega become 2 times. So now this is passing through a band pass filter whose pass band is centered around 2 omega 0. So only this band pass filter will allow signal around 2 omega 0. So that is the pass band for the band pass filter given here. So all DC component, all things are removed by this band pass filter, and this will be only centered around 2 omega 0 bandwidth or 2f0 bandwidth. So that waveform only will be allowed to pass through it. So after, now the signal coming over here will be only cos 2 omega 0 t by plus theta. So that is a signal coming at this point. Now we have, our frequency is not 2 omega 0, it is omega 0 only, right? So now we don't want 2 times, so we have to use a frequency divider circuit over here. It will divide the frequency by 2. So now this 2 omega 0 when divided by 2, it will come back again as cos omega 0 t plus theta. So you recovered your carrier. So first again one more time I will repeat, the received signal, it will be passing through the square law device, so it become cos square theta you can write like this, and band pass filter is centered around 2 omega 0, so that output of this band pass filter will be cos 2 omega 0 t plus theta. Then our frequency is actually omega 0, not 2 omega 0. So you have to use a frequency divider. It will divide the omega 2 omega 0 frequency to omega 0 back. So you recovered the carrier over here. So now the next step is a synchronous demodulator or a multiplier. Here we will multiply the received signal, that means root 2 ps bt cos omega 0 t plus theta, that with your recovered carrier signal cos omega 0 t plus theta. So when we multiply these two, you will be getting this. So that is written over here. So this will be root 2 ps into bt cos square omega 0 t plus theta. That will be coming at this point. Now you have to adjust again, like I'll expand in terms of the same expression over here cos square theta, and then I'll apply it to an integrate and dump circuit, and I'll show you how you will be getting back your original signal BT. So in the next page I'll explain this much part separately. This is the integrate and dump circuit part separately. So now this is the integrate and dump circuit part. So the input coming is here BT into root 2 ps cos square omega 0 t plus theta. No, it's cos square theta. I can write as 1 plus cos 2 theta by 2. Just I expanded that term. And now this signal is being given to the integrate and dump circuit. That is being shown. It is an open based integrator circuit. So here you have a bit synchronizer. What is the need of a bit synchronizer? Bit synchronizer will be able to recognize precisely the moment which the end of one bit interval and at the beginning of the next bit interval. So when the first bit duration ends, and that means at the just beginning of the next, it is, so it will precisely recognize that interval. That is a function of bit synchronizer. That means this bit synchronizer only will be able to allow the switch SC. So that means at the end of the 1 bit interval, whatever the charge stored by this capacitor, it should have to discharge. So at the end of the 1 bit interval, or precisely just before the beginning of the next bit interval, the switch SC, this is the switch SC, it will just close. It will discharge completely the integrator capacitor. So whatever charge of the previous bit, it will be getting discharged. And precisely at the beginning of the next bit interval, this switch remain open. So that again for the entire next bit duration, this integrator capacitor will charge for the next bit. And again at the end of the next bit, this switch SC will be closed and this capacitor will discharge. So that's means that exact the moment will be identified by the bit synchronizer. And again it is having the control to this switch also, this output switch also. So that means at the end of each bit interval, whatever the capacitor is charged, that one, this switch will be closed and you will be getting at the output. After that only this switch will close and this capacitor will discharge. So before the closing of this switch will be closed, and whatever integrate at the end of the bit interval, your output will be coming. And at around end of the bit interval, this switch will close and the capacitor will discharge and it will prepare for the next bit integration. So this is what is doing in this integrate and dump circuit. Now we will see how this output is coming. So at 0 to TB duration, if I am integrating this expression, so that will return 0 to TB duration. So 1 TB, I am just 1 bit, first bit I am just integrating. So it is BTB into root 2 PS integrate 0 to TB. So I am just splitting this expression. This first part is half, second is cos to omega 0 T plus theta. So just multiply inside and splitting up and separately integrating it. So first part, this one, only you have half into dt. So when I integrate this, I get this expression as such. That means BTB into root 2 PS into half into this one. This time nothing is there, just 1. So it is TB. When I integrate, it is TB. Now the second part, when I am integrating on one period, it is cos 2 omega 0 t. So see, cosine, it is, as I told you before, it should be integer number of cosine cycles. So when you are integrating over a period of time, this average value that will be equal to 0. So integration of full cycle of a cos theta, that will be equal to 0. So the second term we will be getting only 0. So you will end up with only this term, BTB into root 2 PS into 1 by 2 TB. So root 2 and 2 cancels. We will be getting the expression as root of PS by 2 into BTB into your 1 bit interval TB. So you will get every bit interval. This lamp just taking the first. So when you integrate each bit separately, 1 bit by 1 bit you have to integrate. So maybe like you can just put it as k minus 1 TB to k TB. So every time you can just put like that, and then you will be, it will end up with the respective bit output you will be getting. So that is about the reception of BPSK signal.